So welcome back. What I said I would want to do now is to try to optimize these parameters, because in reality you will not know the parameters up front. I mean, that's obvious. So what we want to do this, we want to do maximum likelihood. Before we just show that we can calculate the likelihood function given that we run the filter. So if we, for a particular set of parameters, we can run the Kalman filter, and then we can calculate the sum of squared residuals normalized, and then we can calculate, here I do not have the minus as we had up here, but I just have without a minus, because the optimizer wants to minimize and we want to maximize likelihood. So we want somewhere we need to multiply by -1. And the easy one is to not put the minus there. So that's what we do. Now I do one more thing. I'll do it with and without, but first I'll do it the way that is appropriate to do it, and then I'll afterwards show you what happens if you do not do the appropriate thing. So for the variance parameter here, I won't just use the second parameter that I'll try to estimate what is the initial variance, what should that be for the state. I will do the exponential of the parameter. So what does that mean? What is the feature I get by using the exponential of a parameter rather than using the parameter itself? When you look at the numbers that comes out of the exponential of something, it's always positive. So you will never get a negative variance. Whereas if you do not have this, you may actually run into problems. But I'll show you how it fails in a moment if you did not do it right. Here I also have for the parameter here, what is the initial height? I did not need to do the exponential there, because I mean the number 10,000 is so far away that it would probably work fine without it. So I'll define this function, and then how many of you have not used the optim function? Quite a few. Okay, so optim is an optimizer. It can use a ton of different methods. I will use the BFGS algorithm. It's a line search method. If you want to know more about it, optimization data fitting is a course that focuses on how to optimize things. Anyone took? I mean, I think that should still be in there. Sorry. Memory? Fine. Good morning. Basically what you do in here, the optim function, you have to give it the initial parameters, the function you want to optimize. If you want to give it a gradient as well to work with, depending on which method you use, then you can do that. And then you have the different methods you can choose. And that's what I'll do right now. And you'll just optimize. First thing is to look, you want to have this word here, convergence. That's a nice, because you have a nonlinear optimizer. It may not actually get to an optimum. It may be trapped somewhere. If it's not nice and convex and things like you mentioned earlier as well. So what did we estimate? We got an objective function of 252. It's actually very close to what we got with the just before. And then we get some parameter values here that are, you can say, not that meaningful because they are in the log domain. So we want to just look at that instead. And then we see that, okay, the estimate here is to start at 10,028 meters, where the true value of using the simulation was at 10,000 meters. And with a very, very small variance, but not zero variance as we did before. So that's the optimal setting. Now, as I have a comment here, as for illustration, we'll do the same thing, except that I do not have the log transformation of the parameters in here. So I just have the second parameter for the variance and the first parameter for the state. Let me define this function and then run. Everything is the same except that I don't have the log in front of here to transform my estimates to something. It fails. Because the logarithm of something gives you an NaN. So when does log give you not a number? Do you know? Exactly. Log of -1 gives you that warning. So that is what happens. The variance becomes negative somewhere. We don't want that. So that's also the reason why I use the LBFSB, because that you can bounce. So I'll just say that the lower bound should be 0. So then I won't have negative variances. The objective function is the same. It will converge. That's nice. And the optimal value is also close to the same thing. And the parameters are roughly the same. But the variance here is actually, the estimate is 0. It's on the border. As such, it's not a problem right there. Other places, you want to make sure that you have positive variances. And then you need to set the lower bound not at 0, but 10 to the minus. What is the good value? That's a subjective choice. And you're likely to kind of hit that boundary, as we did here with the pure zeros. Now, I think now we just estimated the variance. I think it's more relevant to also estimate some of the parameters in there. The one parameter that is in here is the gravity. So if we do the same thing where we have a third parameter that is the input up here, which is just g. How does that work? Let's just do it. And again, I have the exponential everywhere, so I'm sure that things are positive. Of course, there may be cases where you want things to be positive. You don't have to do the exponential of every variable. You can do it for some. But then when you want to present your result, then you should not just do exponential everywhere. Then you should just do it for those that matters. So I did it just because it's easier. So I will run the optimizer again, starting somewhere with an initial guess of 9 for the gravity acceleration. In this case, I get an estimate of 10.2. Not the usual number, but why do I get such a large number? Maybe that's not a fair question. I will, just for fun, go back up here and re-simulate the whole thing. Oh, I should not take the seat with me. Let me just do some random. I'll just do it twice now. That's fine. I just want to make sure that I don't get the same numbers as before. Oh yeah, so here you can see how much before, initially when we do not have a lot of system noise in the process, the velocity was just a straight line. Now you can see the velocity is bouncing up and down a little bit. Now I think we can go down and do the same optimization. This one here. Now I got 9.4. So because of the system noise being so big in this case, then we do get a lot of uncertainty there. If I go up and reduce the system noise to the initial part and re-simulate. Oh, I have to re-initialize first. Everything. Now you can see that the velocity profile is just linear increasing. If I go down again and do the optimization, have to go down to the third one. That's the one. Okay, I actually got a large number again this time. Now, but 10.1 is not too far away from 9.8. I mean, we should keep in mind how numbers are. Just for fun, I have not tried this before. I want to see, now let me finish and then I'll go back and do what I'm thinking of. What if we just lost all the observations again? Which estimate would we get? I think that would be an interesting thing to try. To get, as mentioned, you want to look at the Hessian in order to get the uncertainty. So there's a package called numerical derivatives, or numDeriv, and then I will calculate the estimate of sigma hat, which is the objective value, divided by the number of one-step prediction errors that are included. And then the estimated variance for the parameter vector is 2 times sigma hat times the inverse Hessian. We have it here. What we usually care about the most is the variances, so we'll take the square root of the diagonal element. So the uncertainty on the height, initial height, is very, very small. It's very well estimated, whereas the uncertainty on the initial variance is quite uncertain. If I want to do a confidence interval for this, I pretty much just take the parameter and I have plus minus 1.96. Now you have to keep in mind that this was for the original model where we did everything in the exponential domain. So I have to transform back to the original domain. So what can I say about the initial covariance? Nothing. I cannot say anything about it, actually. It really doesn't matter that much what the initial covariance is as for the objective function. Pick a number between 0 and infinity. I mean, within 95% confidence, it's equally good. Of course, there's a number that is better, but the initial height is, however, quite well defined. If we do for the second model, where we started off, when we had this estimate here, that was the untransformed situation. We do the same thing. We fail because of the negative. Because I did not rerun that estimation, and then I get something too long. I know why that didn't work out. I'll go up and filter, rerun the filter. Again, that is what happens when you redo your simulation and you have a variable number of observations in your vector. That is what happens. So let's just take them all once again. So this was the second. I still get not a numbers. I thought that would give me a positive one. What did I do wrong? My sigma hat is positive. That's why. My estimate of the Hessian here, because of the optimum not being well behaved, I get a negative variance. That's what happens when you just do a numerical estimation of a Hessian. It depends on your simulation what happens there. So you do a Hessian around 0, and you know if you use negative numbers, then you have a problem. So that's why it fails here. When I ran it yesterday, I got, I don't know what the reason is, I did get a number here, and then I would have still a very large uncertainty on the variance estimate. So that means the confidence interval will run from, yesterday ran from minus 150 to 150. So the confidence interval included a negative value. So that's another reason for, I think I argued very well that you need to transform, when you have variance parameters, you need to make sure that they're they're positive, or zero at least. That was the main reason for this. So I actually managed to fail even harder than I planned. Probably due to some of the other changes that I've done further up. But that's how life is sometimes. So to get back missing data, of course, that doesn't not only happen when you're doing filtering. We still want to identify the models. We still want to calculate the autocorrelation function. So we'll have a small helper function called A that is an indicator function, which means that it's a 1 if yt is observed and 0 if it's not observed. And then we'll basically just calculate for particular lag how many pairs do we have. Because if both are included, we get a 1 here. If one either lag t, time t or t plus k, then that will give you a 0. So basically what this is doing is just counting how many pairs are there, and you divide by n. So it indicates how large a fraction of the possible pairs in the autocorrelation function are actually available. So if it's just one number that is missing, then you would have, you can say up to the order k, you just have one element missing everywhere. So this is for large n, it is the fraction. Of course, for smaller n, it's not totally the fraction, because you divide by n, but you only have n minus k elements in the sum. We discussed that. Don't calculate the autocorrelation function to a large number relative to n, because then they're just going to 0. So how do we use this? Basically, we calculate the mean value, and that's just a weighted sum of all those that are observed. So we just take A times the observation divided by the sum of those that are observed. So this is basically a way of saying I just take the sum of all those that we observed and divide by how many we observed. Now the autocorrelation function here, we define this C with a box here, where we have the usual suspect out here with yt minus the mean value times yt plus k minus the mean value of y. And then we pre-multiply by this indicator of whether that pair is observed or not. So basically, it just means that we only add elements to the sum when they are observed. You can code it saying that we only take those pairs that are actually there, and just say that if you have in R, for instance, if you have an NA in one of the observations, then you just do the calculation, and then you do the sum where you remove NAs, and then you count how many were actually observed. That's the same thing as what is done here. Again, we divide by n, and then to estimate the autocovariance, then we divide this here, not just with the n, but with the proportion of the possible pairs that we actually took into account. So basically, we just do the sum of all the possible pairs divided by the number of pairs, because the division by n here and the division by n here cancel out. So that's what you do, and if you do the ACF of something, and there are NAs, it will give you an error of some kind, unless you say that the NA action is to say NA.omit. That's doing exactly, take everything that you, use everything that you can, and normalize with the appropriate thing. So that's what you do, it works. Now, the next thing is, we won't have time to do that. You can also have the coefficients. So far we've assumed that A and B and C are constant? What if they are not? In practice, things may change over time. In practice, in particular when you go to nonlinear models, you will often say that there's a parameter, I don't know what that parameter is. So what do? I add that parameter as an extra state. It could be that, I don't know, it doesn't make sense in this case. But the problem is when you have a parameter that you add as an extra state, say here, and you want that to be used by the other parameters, then you make a model for that parameter, but you want the product of the two to be part of the result. So then it's a nonlinear model. So in practice, with the linear models, we cannot do that. We can only do it when we don't want to have a product with what is outside. What I find is one model where this is interesting to do, and if there's time, I will show you how it works, although I did not fully prepare it, so we'll just take it from there. So we've all done linear regression. Some of us have done it many times. And when we have things evolving over time, we have observations that are changing. The dynamics of the system may also change. So the relation between the input and the output may change over time. Say there are seasonal variations, and the question is, when you sample hourly data, do you actually need to make a model that takes care of the season? Or is the season sufficiently slow so that if you just make a model based on the most recent data, everything works out fine? So that's the strategy. Now, think of, where did I put it? Think of the Kalman filter. What we want to do is linear regression. What we want to assume is that the observations that we have at time t is some slope at time t times what is the input at time t plus some intercept at time t plus some noise. Let's say this is actually what we want to model. How do we do that as a Kalman filter and use the Kalman filter to estimate our parameters here? So this is the goal up here. So if we define the alpha and beta as our states, at time t, it should depend somehow on what was there at the previous time, alpha, beta, t minus 1, and we should have plus some noise. Maybe we can write it in many ways. For now, let's just write I'll write an ET here because it's a different error than the error up there. Now, if we have this system, we get back to what to write in there. If we have this system here, then we need to write an observation equation. That should be observing yt. Now, what should we then do? We should have something here, and then we should multiply. If we go for this, we have a ct, and then we have the state, that is alpha beta at time t, alpha beta at time t, plus the observation noise up there. So what is left right now is to figure out what to fill in here and there. So in order to represent this model down here, alpha should be multiplied by the input x. So this is not the state x, that's the input for the linear regression model. So that means that I should have xt there. Beta should be multiplied by 1, So I just need to add a 1 there. So this gives me a representation of this linear regression model. And what I have to do is I just have to update my observation equation each time, so this matrix is updated with the adequate observation. So what should I do up here? I can do whatever I want to. I can make whatever model I want to for the parameters. The traditional thing to do is to do like this. So which model is this? What would you call this? What is the model for alpha and the model for beta? Yes? They're independent. They're totally, well, depending on what the covariance is for this one. But let's assume that that's a diagonal matrix, then they are independent. True? Would you call this, are these belonging to any of the ARIMA classes? Yeah. Let me just rewrite for the alpha. Basically what it says there is alpha t equals alpha t minus 1 plus, I call it e alpha t. That's basically what it says here, right? Likewise for beta. So what is this process? You've seen that before. The only difference to what we've seen before is this. It's a random walk process. So what we say is that we allow the parameters to perform a random walk, and then by observing how they relate to the observed output, then we'll estimate these parameters. It works. Works fine. But you can also make more complicated models in here. Because remember that in this case we just had a random walk model, but we can take any ARMA or RIMA model and write it on state space form. Basically, if you want to do that and want to make a RIMA model for alpha instead, you just take, instead of having this 1 as a single number, you make a block here for the model that you want for alpha and the corresponding vectors here. And then you just pick only to use the first element there. Does that make sense? Basically, we can consider this here as a vector and a block matrix. And then you can go back, far back in time, to here. And then you can have this structure here of matrix as the block there for alpha, and similar for beta if you like. So you can do any kind of model for each of the parameters here, if that's what you want. So it's quite flexible as to what you can do. So that's the time varying system. And the Kalman filter, it's basically just the same. The only thing that is different is that everywhere where there before was just a constant A or B or C, and likewise for the covariances, it contains a subscript of time. So which observation equation you're looking at, what is the appropriate version of it to use. That's all there is to it. All the rest is the same. So you can fairly easy implement this. I did implement it, but using a totally different library than what I want to share, because it's quite difficult to understand what actually goes on in there. But it's a very flexible package. So maybe I'll do it after, or to just time, and then just see how it goes. Now, as a different example, if you have an AR1 process with observation noise, let's just think of you have a surrounding temperature, and then you have a temperature that you want to model for this room or body or whatever. And then we have the differential equation for this, assuming that the surrounding temperature is 0. It's a good approximation for today, at least. Maybe even better yesterday outside. The solution for that differential equation, we've done this exercise, I think it was last or the week before, on the blackboard, to say how do we go from a continuous time system to a discrete time system. We just have to sample that, and then this becomes our transition matrix A, uppercase A, that we've done previously. It can work both univariate and multivariate, but that's what we have. So if you then have some noise to it because of, you say, whatever, then we have a system equation here, and then we can observe it indirectly with some noise. So let's take this model, and if we, just for fun, simulate this, then we get this. But let's go back to the model. Which ARIMA model does this represent? It's an AR1 model that we have down here, and then we observe it with some noise. Can we represent this in a similar way to what I wiped out here before for the MA model that we have with some noise? What if it is an AR1 model that we observe with noise? How does that work out? So what do we have? How do we get around looking at this set? Basically, what we want to do is to look at yt, and then we know that xt we can isolate. Also, here is the temperature is T. So we have this equation here: yt equals T subscript T plus eta T. That is equivalent to say that Tt is equal to yt minus eta T. That's fine. We can also use the other equation that we have and say that yt is equal to, well, Tt. We have an equation for what that is up there. So that is minus phi t minus 1 plus et. So that's that term up there plus eta t. And now to get rid of this uppercase T here, T minus 1, we just use this up here and shift that time, one time lag. So we have yt equals minus phi, and then I have yt minus 1 minus eta t minus 1 from up here. That was that part. Then I have the plus et plus eta t. And if I continue this, just multiplying in, then I have minus phi yt minus 1. And then I get a plus phi eta t minus 1 plus et plus eta t. So what is this model? We do I won't go through the calculations, but we have the same structure out here that we have, you can say, two noise signals that we add. We can treat them as one. So we just have a larger noise here, and then we have part of the noise here, effectively. So which model structure do you have? This is an ARMA Yeah. It's a 1,1 exactly. So basically what we have here is that we have an AR1 model, and then we add some observation noise to it, and then we get a moving average part on top of that as a gift. But it's just again to underline that whenever you observe something with noise, you should not expect that what you observe there is not the underlying model structure. It's a different model structure that you're identifying. So you're always adding something to it when you do this. So that's just, once again, no matter what you have, it becomes, I would say in general, typically you get one extra order somewhere. And if we look at this, the ACF has an exponential tail, and the PACF also has an exponential tail, which is in very good correspondence with it being an ARMA 1,1 model, right? And the drop here in ACF from like 0 to like 1, that is exactly coming from the moving average part. So we've looked at ARMA models and state space form, what happens when you add noise to it as well to make it more general. What happens when you start handling missing observations, predictions when you have missing observation, prediction in general, likelihood estimation, and also you can say how to optimize things and how to compare different models. Now, what I said I would, in case of time, there are two things that I could find was interesting to do. One would be to say, what is the likelihood when I have missing observation? How does that work when I optimize? Will I actually still get something? And the other one is to actually implement this part up here. And I think I will do the first thing is fairly straightforward. Because what I have to do is to go up and get my first objective function up here. I'll just copy it down at the bottom and say, what if using missing, using data with missing observations. Let me just check. So Y part is still defined. So basically what I'll do is I'll take and use the partial observed data in here instead. I'll call the objective function something different, not to override my previous function and screw up everything. So I know that my filter will run. Now my problem here is, and that's where indexing is always a challenge. What do I want to do? I want to calculate my observations minus the predictions and my prediction errors. What I do down here is I do a sum of all those. And then I do the log of the prediction variance. So this last bit here is the prediction variances, yes. So I think if I do it right now, what will happen is that this vector here, maybe I should, can I do it easily showing you? I think everything is defined except for the parameters. So if I just define the parameters here as the log of 10,000, 10, just to say something, that's the variances, then I think I should be able to just run subscript out of bounds. What did I run out of bounds on? Ah, that's because I have y there as well. So now I have what comes out, and if I run, look at all the prediction errors, I have, these are my sum of squared prediction errors normalized by the variance that are associated, and if I calculate this sum here, I get NA. So the only thing I have to do as well is to say that this sum, that's the log, that sum there, I should just ignore the NAs. Then I get something. So since this is, now I just get the sum of all those that I observed. So let me just define this function. And then I will do that to my partial, and my objective is now called dot part. It converged. I'm happy. And what did I get out? This was the case. I get not 10,000, but 10,500 meters. So I got quite a different estimate, I would say, to some extent, but not too far away. And I still got a very small initial variance. So I'm still able to estimate things. And if I also went to use the function where I estimated gravity, but I know I should probably add what are the standard errors of these. So I just need to take the dot part there, and the objective function is also dot part, and then I should not divide by length of y, but what should I divide by? How many predictions do I actually have that are meaningful? I have the is not NA minus the first one, yeah. So that would work. Then I get a covariance matrix, and I got a negative there. Why did I get that? Because I used the wrong parameters. So I again get a very small standard error here, and I should also, again here, I should do the exponential of this when I get the prediction intervals. Let me go up and take the one that's on the right scale. Dot part. The parameters from there. And there should be one more place. Nope. So actually in this case you can say the true starting point is actually not including the 95% confidence interval. But we also only had very few observations in this case. But it's still, I mean, in the neighborhood. So we're doing okay. Now, what was y part? We observed the first one, and then we did not observe anything until the 10th one. So we have one observation, and then we wait a long time before we get any more. So our initial condition is not that well defined as such. But still, we get in the neighborhood. So just to say that it's quite flexible. I think there is